Hello and welcome to Unit 7. This is the last part of Unit 7, and we're going to bring in yet another concept, and that is the concept of power, which is very closely related to energy. You may remember in the definitions we looked at that there was a lot of references to power in there. Okay. Really quick, as an aside, again, the unit of power is the watt, and by definition, 1 watt is 1 joule per second. Now, another little bit of caution. We ran into this a bit in a different video, but we have W's everywhere. We have something that looks like Earth on object. Well, this W is a weight. We have this W, which equals, say, F delta R cosine theta. That W is work. And now we have another W, say like 60 watts. This is a unit for power. So we have W's everywhere. And it can get confusing. It can get very confusing. So one thing I'm going to say is you can usually tell your W's apart by context. Where does it fall in the equation and stuff like that. Weights, when I use them, they have subscripts, so that makes it easier for me as well. But feel free to get a notation that works for you. If you want to make sure that, hey, this one's a capital, so there you go. This one might have a little flag off the front so that you can tell it from the other one. Come up with something that works for you. Okay. Now, by definition, average power is the change in work divided by the time it took for that to happen. Okay. If I want just power, that is found through the differential, not a huge surprise given that we know that often deltas turn into differential elements on the small scale. Or you could rearrange this, and if you know the power, integrate to find the work. We're going to now look at 2 examples using power. And the first question we're going to ask is, how much energy does a 60-watt light bulb use in 1 hour? Okay. So, power is going to be, on average, change in work divided by change in time. In this case, I want to find the work, so that will equal power times time. We know it is a 60-watt bulb. In 1 hour, 1 hour is 3,600 seconds. And if I take 60 times 3,600, I get 216,000 joules of energy used by a 60-watt light bulb in 1 hour. Now, it seems like a big number, but typically we don't use or don't measure energy usage in units of joules, because joule is too small. So typically, instead of seeing this in the power usage for your house or something like that in units of joules, you will see the unit instead to be kilowatts times hour. So they increase the unit here and they increase the unit there. If we do that and convert our units, 60 watts would be 0.06 kilowatts. And then we can just multiply by 1 hour to get units of hours. So equivalently, this would be 0.06 kilowatt hours, which, if you look at your power bill, which is really an energy bill, that doesn't seem so bad. For our next and final example, we're going to consider a 60 kilogram adult running up a flight of stairs in half a minute. We're going to assume that a flight of stairs is about 10 feet or about 3 meters. And we want to know, how much power does the person exert? Right? Okay, well, here's the thing. To really determine how much power the person exerts, what we would need to know is the normal force between the person and the ground, and we need to know, is this person accelerating up the stairs? We would need to know more information to really be able to find this. But we can put a boundary on it. Okay? If we assume that the person runs up at constant speed, then the normal force between the person and the stairs will equal the person's weight. And that is going to allow us to put a minimum bound on this answer, right? The normal force could be bigger in order to accelerate the person up the stairs, but at minimum, it has to equal the weight for the person to go up at constant speed. Okay, so now I can find the work as the force times the displacement times a cosine of an angle. We just discussed how the force will be weight, which equals mg. Delta R we're given, that's that 10 feet up there. And the angle here, technically weight is going to be opposite the displacement, but the normal force will be in the same direction, so the angle will be 0. So we have 60 kilograms times 9.8 meters per second squared times 3 meters. And this works out to be 1,764 joules. To find the power, I'm going to take the amount of work done and divide by the time interval. So that would be 1,764 joules divided by half a minute, which is not half a second. Let's try this again. Half a minute is 30 seconds. And that tells me that the person must exert at least 58.8 watts of energy. Might exert more, but at least 58.8 watts of energy. And this concludes this part. It also concludes this unit.